Asymmetric structure. In order to illustrate some asymmetric features in TCs, Figure 3 shows two hurricanes, Hurricanes Dolly, 2008, and Alex, 2010. Hurricane Dolly was very asymmetric in the inner core region. Note the azimuthal wave number 4 pattern in the eyewall radar reflectivity. Hurricane Alex, 2010, was also very asymmetric, and had a large spiral rainband emanating from the core, and no visible eye. The point illustrated here is that TCs come in a wide variety of shapes and sizes, and often have prominent asymmetric features. While there is some structure dependence on intensity, i.e., stronger TCs in general are more axisymmetric than weaker TCs, at any initial time a given TC may have very different structure, and the goal of the initialization system is to capture its true state. Remote satellite measurements generally give a decent estimate of the horizontal structure. In fact, microwave data has allowed the ability to see through visible and infrared cloud shields, giving improved estimates of the deep convection and precipitation. However, typically there is much less data about the vertical structure. For example, the boundary layer structure or convective and stratiform heating profiles of Alex's rainband would not generally be known. Due to the lack of observations in TCs, in TC initialization systems, aspects of the structure are often specified using estimated information from satellite images. Radar and visible satellite imagery depicting asymmetric features in TCs. Hurricane Dolly, 2008, left panel, had asymmetries in the eyewall and rain bands. Hurricane Alex, 2010, right panel, had a large azimuthal wave number 1 spiral rain band propagating outward from the vortex center. The left panel is courtesy of the NOAA National Weather Service and the right panel is courtesy of the NOAA/NSDS in Fort Collins, Colorado. Direct insertion schemes. As discussed in the previous section, TCs are poorly observed, particularly in the inner core region. The North Atlantic Basin is the only basin that routinely has aircraft reconnaissance missions into storms when they are close to the U.S. southeast coastal regions. The aircraft reconnaissance missions can provide important inner core structural data using airborne Doppler radar and dropwindsondes, as well as direct or remote measurements of surface wind speed and minimum central pressure. Due to the lack of observations of the inner core structure of TCs, vortex bogussing has been used to improve the representation of the TC in numerical prediction systems. Generally speaking, vortex bogussing is the creation of a TC-like vortex that can be inserted into the initial fields of numerical models. The direct insertion methods take a bogus vortex and insert it directly into the numerical model initial conditions. The bogus vortex can be generated in different ways, which are described below. The main strength of these methods is that the vortex is usually self-consistent. However, some weaknesses exist. First, there can be imbalances that may exist when blending the inserted vortex with the environments in the model analysis. Secondly, for weak TCs and TCs experiencing vertical shear, it is not desirable to insert a vertically stacked vortex into the initial conditions, which is often the case with bogus vortices. Additionally, previous studies have shown strong sensitivity to the vertical structure of the bogus vortex, which is often not well observed. After a bogus vortex is created, there needs to be a method to properly insert this vortex into the initial fields of the forecast model. The first guess fields, or the previous model forecast which is valid at the analysis time, usually will already contain a TC-like vortex from the previous forecast. However, this vortex may have an incorrect position, intensity, and structure, and therefore it should be removed from model fields. Vortex removal and insertion methods require a number of steps. The common method, discussed by is as follows. First, the total field, for example, surface pressure, is decomposed into a basic field and disturbance field using filtering. Next, the vortex with specified length scale is removed from the disturbance field. Then, the environmental field is constructed by adding the non-hurricane disturbance with the basic field. Finally, the specified vortex can then simply be added to the environmental field. Schemes of this nature are widely used in operational tropical cyclone prediction models in order to improve the TC representation from the global analysis. Since TCs are observed to largely be in gradient and hydrostatic balance above the boundary layer, one method is to insert a balanced vortex. Routine warning messages are generated by TC warning centers that include estimates of the maximum sustained surface wind, central pressure, and size characteristics, such as the radii of 34 kilotons winds. Using a function fit to the observed radial wind profile, for example, a modified Rankine vortex or more sophisticated methods, along with a vertical decay assumption, one can obtain an axisymmetric tangential wind field in the radius height plane. Following this, the mass field, temperature and pressure, may be obtained by solving the nonlinear balance equation in conjunction with the hydrostatic equation. Then this balanced vortex may be directly inserted into the model initial conditions, as a representation of the actual observed TC vortex. While this method is relatively straightforward, there are a few potential problems. TC vortices are not balanced in the boundary and outflow layers, where strong divergence exists, and, 2. In convectively active regions of the vortex the hydrostatic balance assumption is not valid. It is possible to relax the strict balance assumptions above by building in the boundary layer and outflow structure diagnostically. The addition of boundary and outflow layers should reduce the amount of initial adjustment after insertion. Instead of specifying a vortex, usually analytically, to represent a TC, another method is to spin up a TC-like vortex in a numerical model in an environment with no mean flow, and then insert this vortex into the model initial conditions. This method is called a TC dynamic initialization method because the TC vortex is developed from numerical simulation of a nonlinear atmospheric prediction model with full physics that requires prior model integration. The benefits of such a procedure are that the numerical model will generate a more realistic structure for the boundary layer and the outflow layer, and the moisture variables can also be included. The TC dynamic initialization is usually accomplished through Newtonian relaxation. A Newtonian relaxation term is added to the right-hand side of a desired prognostic variable, for example, the tangential velocity or surface pressure, in order to anchor the vortex to the desired structure and/or intensity. The Geophysical Fluid Dynamics Laboratory hurricane prediction model uses an axisymmetric version of its primitive equation to perform the dynamic initialization to a prescribed structure. Recent work has also shown encouraging results with the TC dynamic initialization method using an independent three-dimensional primitive equation model in conjunction with a three-dimensional variational, 3-var, data assimilation scheme. In Figure 4, a flow diagram is shown depicting a TC dynamic initialization method applied after three-dimensional variational, 3-var, data assimilation, where TCs are spun up using Newtonian relaxation to the observed surface pressure. This procedure showed a positive improvement in TC intensity prediction, as average errors in maximum sustained surface wind and minimum central pressure were reduced at all forecast lead times. Application of a TC dynamic initialization scheme to a 3-var system, reproduced from. A TC is nudged to observe central mean sea level pressure, MSLP, in a nonlinear full physics model, and then inserted into the forecast model initial conditions after 3-var. Copyright 2011 AMS, http://www.amitsoc.org/pub/chronotis.html